Okay, it's 8:30. Let's get going. So before I do the new stuff today, are there any questions? All right. So what we're going to do today is discuss the beam problems. Okay, I think it's chapter 7. It starts in chapter 7, and there are some issues that are going to arise, and we're going to look at it in this form, A, B, and C. So let me give you an example. If you go back to your deformable bodies course or stress analysis course, when you were given, for example, a cantilever beam fixed at one end, that's what cantilever means, and then let's say tip loaded at the other end. All you did was to draw a straight line, okay? And then based on the stuff that they taught you, you calculated the deflection, you calculated the stresses, etc. But remember, when you draw a straight line, if, for example, my cross-section is rectangular, such as what you see here, when you draw that straight line, you don't say how the cross-section, you know how it looks like, but how it's oriented. For example, if I make that cantilever beam from that orientation on the second one from the top, or the third one from the top, or the fourth one from, they all deflect differently, okay? The only thing that doesn't matter is a circle. Circle, it doesn't matter how you turn it. It makes no difference. This is why when you do beam problems, the easiest case that you can have is a circular cross-section, because you don't have to worry about the orientation of the cross-section. But if it's anything but a circle, you have to tell the software that there is a point which determines the orientation, and we'll get that to the second. Let's put it this way. Hope that on the test it's all circular, because otherwise you have to create that orientation point and select it so that it puts it in the right perspective. All right, let's move on. I'll show you how to, for now, I'm going to make a circular one. I don't want to worry about that, but towards the end, I'll show you about that orientation point, how do you specify it, etc. Now, here's the situation. We solved this problem about 10 days ago, first day of class, okay? There, I had a bent rod with a circular cross-section. The bottom of it was clamped, and then I apply a load so that this thing twisted and bent, okay? And this is the kind of problem that you did in your stress analysis class based on energy approach, okay? And I modeled it with solid element, and I said that this is not the good way of doing it unless you're absolutely sure you want to get the stresses. Because if you do beam problems, like you did in stress analysis, something is going to give in, okay? For example, the stress distribution is not going to be exactly what the real-life stress distribution is, okay? Deflections are okay. Bending stresses are okay. The MC over I, MY over I, those are okay. But there are shear stresses. There are other things that in beam bending we ignore. Anyway, what I'm saying is that yes, you lose something if you use beam elements to model this problem. However, in many situations in real life, these beams are primarily used to transfer the load. You design it so that they don't fail, but they transfer the load. So I don't care about the stresses in the beam, for example. I may not care. This is why transferring the load through beams is very common. All right, let's move on. The way it works, you draw a line in space. You draw a line like that, just like you did in stress analysis. And you tell the software what the cross-section is. If it's circle, no problem, very easy. And the element, the line is broken into beam element. Beam element are just little pieces on top of that line, okay? Element 1, element 2, element 3, going along the beam, okay? So you can see on the left side, for example, I don't know, I may have 10 elements, 20 elements. You can see that. The middle number gives you the element number. The 2 on the side gives you node number. So this is what we do. And every linear beam element, there are two types of beam element, linear one, parabolic one. Parabolic is more accurate than linear. Not by much, but more accurate. However, if you have a curved beam, parabolic is better because at least you can trace the geometry. Okay, if the beam goes like this and you put a linear, basically you've broken down into lines, and as long as you have a lot of lines, as long as you have a lot of elements, is okay. But if you don't have a lot of elements, then at least try to trace the curve of the beam with parabolic ones. But let's not worry about it. This is a linear beam element. At every node, it has two nodes. At every node, instead of 3 degrees of freedom that we had it before, translation X, translation Y, translation Z, beam elements have 6 degrees of freedom, translation X, Y, Z, and rotation about X, rotation about Y, rotation about Z. And look, this is exactly what you did in stress analysis. In other words, there you talked about rotation. In beams, you talk about rotation at the node, at the point in the beam, okay? Basically, the angle that it makes with the horizontal. So every node of a beam element has 6 degrees of freedom, 6 unknowns, okay? Two-noded element have altogether 2 nodes times 6, 12 unknown variables associated with that one element. Now, some of them you may know. For example, if you clamp one end, you know that everything is 0. Displacement is 0. Translation in all 3 directions is 0. Rotation in all 3 directions are 0 if it's a clamp. Okay? And so, I mean, it doesn't mean that I said 6 degrees of freedom times 2 is 12. 12 unknowns, but not everything is unknown. For example, at boundaries, when it clamps, 6 of those zillion elements, zillion number of degrees of freedom are known. 6. Okay, let's move on. Any questions here? The issue of symmetry in beams, because every problem you will be asked to use as many planes of symmetry as possible, is going to pop up. But before I do that, I want to ask you, based on what you have seen in the last four lectures, in solids, forget about beams. In solids, if you took a plane, you cut them apart with a plane, and that plane was a plane of symmetry. For example, XZ, just hypothetically say XZ was a plane of symmetry. What do you know about the degrees of freedom for a solid element? XZ is a plane of symmetry. What do you know about translation of things on that plane? This is very easy. XZ is a plane of symmetry. It does not move perpendicular to it. What does that make it? XZ, here, this is XZ, plane of symmetry. It does not move perpendicular to that plane. So where does it not move? What translation is known? Come on, XZ is a plane of symmetry. Points on that do not move perpendicular to it. So what translation are we talking about? This is XZ. My hand is XZ plane. Things do not move perpendicular to it. So where do they not move? Say it again. Yes. Normal to it. If XZ is a plane of symmetry, normal to it is Y. And why I said that? Because this is the same rule for beams, except that rotations become important too. The rule is very simple. If XZ is a plane of symmetry for a beam, things do not move in the Y direction, correct? Rotation is exactly the opposite. In other words, translation in Y is 0, rotation is free. The translation in X and Z are free, there it's fixed. Rotation is fixed. It's exactly the opposite. We'll come to that later. You're going to get sort this out. It's very simple. XY plane of symmetry, no translation in Z. For solid, for beams, rotations are also there, so you do the opposite. Okay? For rotation, opposite. If you say 0, for example, 0 displacement in Y, no problem. Rotation, leave it free. but rotation in both the Z and X. The other two make them fixed. We'll get there. Don't worry. Plenty of time. But a week worth of time, probably. Okay, so let's go ahead and make it. I'm not going to worry about dimensions here. Well, I'll use the same dimensions as before, but I'm not overly concerned. I start with a part. Now, there are two ways you can approach beam problems. One is to create the shape, that one line that you draw, or this thing that you draw. You can do it as a sketch, in a sketch, or you can actually go ahead and do it in space. There's a difference between a sketch, you go to Sketcher and draw something and exit it and do something with it, and drawing it as a wireframe in space. Wireframe in space is when determine this point and determine that point, draw a line in between them in space. Determine an arc up there in space. This is not in a sketch. Okay. Depending on how you approach that, there is one or two things that is going to be different. Let me start with a sketch. Okay. So on this vertical plane, I will sketch. The center curve, or some software may call it the spine of that part. Get called the center curve. It looks like this. Please remember, I'm ignoring dimensions to the extent that is not. I don't like that. Profile. Because I'm too lazy, I don't want to draw a circle. Okay, so I want a straight line here. Now, notice that I didn't move fast enough, so I lost that. Let me move this thing out of here. See, I want to go straight here, but I didn't do it fast enough. Accidentally, I let it go further, and it became another curve. That you can fix. Boy, I'm trying to get this thing out, bring it out here. Where is it? Right here. You see, if you are too lazy and you don't want to just do it over, these things will help you. If you want to go straight, click on that, click on this, and then go straight. Look, I don't care how you do it. You need to make something like this. I mean, obviously, this has to be horizontal. That's okay. Make something like that. Okay, so let me first clean this up. Let me make this thing horizontal. Okay, good. I'll put some dimensions here, similar to the one that we had before. So from here, I believe to here was 8. It was 8 inches, if I'm not mistaken. Something like this. And then from here to here was 5. 5. And this radius was 1, I believe. Something to that effect. Okay, 1. Okay, good. Exit. This may not be exactly like these dimensions that I have here. Yeah. Looks okay. Same thing. Okay, exit. There is my part. Now, if you are going this route in Sketch, you are doing this thing in Sketch, you have to join this sketch. You might say, well, what's join? It's all connected together. It will not work. If you go this route, you have to join this sketch. There's no ifs. You have to. Why? Because the people who wrote the code, I don't know, were smoking something, they did it this way. What can I do? Okay, so where is the join thingy? The join thingy is in either in wireframe surface design or generative shape design. I am in generative shape design, and it's right here. See that? Right there. Right there. This is if you are in part design, you won't see this stuff because join is not there. There is the join. I am already in generative shape design. You click on it, it joined this, it was already highlighted, and you don't do this, you can't do the rest of the problem. As simple as that. It's done. Let's apply material to this. So metal. Here's apply material. Metal. I don't know, make it out of steel. I think the properties there was steel on the part, and it's okay. Let me save. File, save management, save as, desktop, new folder, morning, the morning class, lab. I'll call it sketch, with sketch, because I may go and do it with other things. So part one, okay, fine. All right, done. This is your part. So now we go to generative structure analysis, just like you did before. Static analysis. Static analysis. Let me move these out of the way. That's it. CATIA will not mesh it for you. CATIA only meshes solid objects. If it sees something like that, or if it sees a surface later on for shell elements, it's not going to do it. You have to do that. So look at the traffic light model manager, traffic light. I like this toolbar because there's no way you can miss it. And open up this first. It gives you all the elements that you can make. The first one, we never made it. CATIA did it for us because it was solid. We had all the problems that it was solid, was right there. The next one is shell. We have not done shells yet, the surfaces. And then there's the beam. There's no way you can miss it. Beam measure. Okay. You click on it. You select the thing that you joined. If you did not join, you will not be able to pick the sketch. As simple as that. The only way you can pick this is if you joined it. If you go sketcher route. You click on it, it turns yellow, good sign. It says what kind of element you want. I want linear. This is parabolic. I'll use linear. A size, I don't know, 0.6, 0.3, 0.1. These are so cheap that you can make it a micron probably line, because remember, it's just a line, 2 degrees of freedom. Each node has, yes, 3 degrees. Each node has 6 degrees of freedom. Yeah, okay. But let's not be ridiculous. Let's make it, I don't know, 0.2. How about that? Say okay. And would you like to look at the mesh? Right click, mesh visualization. Nothing fancy, just a bunch of lines. If you zoom in, you see that there are node numbers and element numbers, blah, 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 blah. They're all over the place. If you want to see them actually, there is a way, and that is, I believe, you go to the mesh, right click. Let me check this for a second. There's a property somewhere. Hang in there. Is it here? Properties. It's not necessary. No, not there. Let me try this. Property. You can shrink elements so that you can see it. I can't remember. It's not a big deal. If you don't trust me, oh, no. I don't know. I'll find out. You can shrink them so you can see how many you've got. I don't know. You may have 50 there. Okay. So let me check one more thing. Shrink right there. I just double clicked on this. Shrink factor. See? Right there. You don't need it. You can put it back where it was. It really doesn't matter. Let me double click on it. Don't shrink it. Good. Rest of the problem. When this is staring at you, the mesh is staring at you, there's nothing you can do. Deactivate or hide or delete. Deactivate. Okay. Now, the cross section of the beam. You see these? We never touched these because this CATIA did it automatically for us. 3D solid, because it always created the mesh for us, solid object. This is for shells, we're going to do later on. The next one looks like an I-beam. Looks like an eye. It says 1D property, right there. You click on it, it says, okay, what kind of a cross-section do you have? Do you have a cylindrical? Cylindrical means solid, basically. Tubular, by the way, tubular doesn't need orientation either. It's a tube, basically. Anything else, if you selected it, you're going to need the orientation. And in fact, it won't let you proceed without picking the orientation. The only thing that's okay is cylindrical, which is solid, and tube. So let me use cylindrical. This is solid cylinder. And you click on the wrench next to it. Run the wrench. It says, what is the radius? Now, I don't know. I think the radius here was, I can't remember. Oh, radius is 1 inch right there. Radius is 1 inch. So you put down 1 inch, and if you say, well, how did it know 1 inch? Because I put it 2 days ago. Okay, 1 inch, it remembers it. Notice that orientation point. We don't. Oh wait, what is the support? The support is right here. This is the support. This is the thing that you joined. Right there. So it gives you 3 pieces. That's because this curve that I drew had 3 pieces. It showed each one. Now notice that you can close it without picking the orientation point. If this was not a circle or a tube, it would not even. This would be dim. It's going to wait for you to pick the orientation, but not for a circle. Excellent. Bottom is clamped. Here's the clamp. This tip is subjected to a force of, I don't know, something in the x direction. So go to force, select this. In the direction x, minus 1,000, don't remember, what was it? 2,000, minus 2,000. And make sure you take this thing out. This is 0. You can apply in an oblique orientation, but you have to know the components. I'm not applying. I'm just applying in the x direction. Here, you see this? Good. And save it. File, save management, analysis, save as. That directory that I created, morning sketch, analysis. Because I'm not going to mix these up, I'm just going to put it in the same place. Not going to rename it. And then run it. Now, it's okay with me, but on a test, when things get mixed up for you, part one of the other problem, part one of it, if you mix them up, it's going to be a disaster. Done. Deflection, right there. Animate, at least nothing grossly is done. The top piece goes through bending. The bottom piece goes through bending and torsion. Okay, it does. If it went somehow in a weird direction, there's a problem somewhere. Deflection, displacement. There we are. Let me make it colorful for you, right there. Anything that you don't, if these are bothering you, hide them. There. And you can animate it. Color looks good. Deflection 0.04 inch, maximum deflection 0.04 inch, which is at the tip, you know that, etc. Notice that it won't let you plot the stress. The stress is dim. 1 meter stress is dim. You can see that right there. Why do you think the 1 meter stress is dim? Let me ask you this. Why do you think stress in general for a beam element is dim? There is an area. The area that radial cross-sectional area, I gave it. It knows it. He knows what the area is. But let's move on. You're on the right track. But if I ask you, what is the stress in this beam? What would you tell me? Stress where? If you go back to your stress analysis class, the stress was linear. At the neutral, for example, for beam bending, the stress at the neutral surface was 0 if it's pure bending. And it gradually grows. Biggest on the top, biggest at the bottom. So the reason that they did not, some software allow you to do that, they decide on some specific point and say stress, I'm going to show you the stress there. But stress, for me to ask you what is the stress, you have to ask me where. Is it on the top fiber? Is it at the bottom fiber? Is it the neutral surface? Is it halfway between the top and the bottom? That's why they decided not to include the stress there. You can plot the principal stress, but unfortunately, the principal stress is going to be the one that they give you. The axial stress is useless. Axial stress. Usually when you do bending, we are not that interested in the axial stress. You can do principal stresses. This is it. Right where your deflection is, principal stresses. But look, what are you getting? The color looks okay. First of all, they're like that. But what is the values? What are the values? 10 to the minus 11. Because none of these members have an axial load in them. One of them twists and bends, the other one just bends. Axial load in it is 0. What good is that going to do me? Anyway, so principal stress you can plot, but it's kind of useless. There may be certain situation that you're interested in. Any questions? Let me also tell you that it is very unlikely in a real-life problem you can solve a complicated problem, complicated real-life problem with one type of element. Usually you have in it beam, solid, and shell, all of them participating. And those we're going to do the last week of classes before the midterm, okay? Before the midterm, so called hybrid element. Right now, you're either only having solids or either having or beams, and later on next week shells, okay? But generally speaking, usually these have to go together somehow. But if you look at this problem, this is this plexiglass in front of me. These can be modeled as beams. This thing, this glass, can be modeled as shell. You can do it with solid, but look at the thickness, half an inch, a third of an inch. Try to fill this thing with those elements. So people do it with shell, okay? And there is something complicated down at the bottom. I can see it there. Maybe some bulky object and things like that. Then you have to do solid. Together they have to work. Okay. Any question about this? I want to go and do the same problem with a different cross section. Yes.
So how is it element like that? How does that resemble something in real life? Because there's no cross section.
There is a cross section. Let me ask you this: a stress analysis class. You don't have a cross section, you drew a straight line, right? Did you not just draw a straight line in Dr. Green's class, whoever taught you? But didn't he tell you what the cross section was? Rectangle, circle, because you calculate an I based on that, or area based on that, if there was axial load, for example. And you didn't draw the cross section, but you were using it in your calculation. Here, it is using it in the cross section. The cross section, I did it. Whereas on the properties, just so that you won't block your view, it's there. It's using that stuff. Okay, so it is there. Okay, now notice that this problem had no planar symmetry, right? Had no planar symmetry. Obviously, when we did this problem with solid elements, we did not have any planar symmetry. But I told you, if the load is applied in the y direction is along that top member, y direction. This thing it comes towards you. This goes towards you. If you apply the load along this direction, and it's very easy to check. Let me see for a second. Let me go to load. Where's my load? Static case load. Distributed. Instead of in the x direction, let me put it in the y direction for you. This is 0, and this is 2000 in the y direction now. Okay, so obviously if I run it, the top member, primarily is axially loaded. The bottom member, primarily it is bending. Not torquing, okay? And you can look at it, okay? It's coming in that direction. You see, it's coming towards you. Let me hide these things. It's coming towards you. It's not going sideways. If the load was sideways, it would make this thing torque, and it go. The point is that you might say, oh, wait a minute, if it's coming towards me, don't I have a plane symmetry there? If it's coming toward me, it doesn't go to the left, doesn't go to the right. Yes, but you don't cut a hair along the length of the hair. You can cut it perpendicular to the hair, not along the hair. Beams, you don't cut them like that. You don't cut them along the beam. There are problems. For example, if you take a a simply supported beam, simply supported, like that, or clamped at both ends. And I put a load here. Yes, there is a plane of symmetry here, perpendicular to the length, and you cut it. Okay, but you don't cut the beam along the cross section like that. You don't cut it like this. Anyway, I'm just letting you know, okay? Because there is a plane of symmetry here, but beams, you don't cut them along the length. You understand? Hair, along hair, there's no way you can cut it along the hair. It's not feasible. Okay, so let me already, these are already saved. So I'm going to go and do the same problem. We have 20 minutes. So we can do a lot of things. Okay, so let me close this. And let me close that. Let me start another one, a part file. I'm going to do the same thing, except that we will take the cross section to be a rectangle so that I can see it actually. Okay. Like if I take it as a square, it may bother you. I'll make it a kind of a long rectangle so that you can see things. So, by the way, I am in generative shape design right there. The only reason I'm there is that because I want to join it. I can go to the part design, but if I go to the part design, I have to come back here to join it anyways. Okay, so I'll just do it there. So on that vertical plane, I will sketch. This time, I'm not going to worry about any dimensions, okay? Because we already know what the story is. Okay, good. Exit. Join. If you don't join, you can't do this problem. Okay. Apply material. By the way, if you don't apply material, you can still go mesh it. But then when you try to run, it's going to come back said, field unknown. Some material is not applied. So how is it going to, work it out? People forget to do that. But first of all, metal, I'll use aluminum. It really doesn't matter. That's not really the point here. Now, I will create a few points for you. Few points, because I want to show you when I select these different points, how the orientation of the beam changes. Okay, so for example, I'll make one point. Let me go along the X direction. So you can see that right there. Actually, let me make it a little bit smaller so that we can see it. That's one point. I'll do another one. This one going, for example, along the Y. Again, 3 along the wall. The actual coordinate makes no difference. The only thing is that orientation point cannot be on that curve or on the continuation of the curve. That's the only restriction. Okay. Here is another one. You can see. I'll do another one which is kind of both coordinates are present. So 3 and 3. How about that? Because I want to show you what will happen if you declare the cross section as rectangular, for example, and then you have to pick an orientation point, how this will be affected. Okay, so we're done here. We're going to go to, and I'm not going to save any of these, okay. Where is it? Generative structure analysis. You mesh it first. Remember, if you had not joined, you would not be able to pick. I'll use the same size. Now the cross section of the beam. Now you have to declare the cross section. Let's make it cylindrical. No problem. I can close this. I can select it and close it. It'll give me those same circle because the radius has not changed. But I don't want to do that. I want to make it rectangular. And dimension, it says, what are the dimensions of this rectangle? So think about it like this, because in real life, if these points are not random, the Y and H, you see it's asking about Y and H. The Y and H are actually perpendicular to the beam. So the beam direction is called X. The Y and H is perpendicular to it. So those points, you can figure them out if you know the shape. Okay. But anyway, let me just put here, I'll just put down a 1 and a 2. So it's a rectangle size 1 and 2. Say okay. Notice that I can't even close this because it says, where is your orientation point? So let me start with this guy. Oh, support, I forgot to select support. I did everything but the support right there. Ah, there. Look. So on these three pieces, the orientation looks like that. If I select a different point, such as this, watch those red things, they're going to turn around. You see? Is this what you want? Maybe it is. If I select this point, it completely kind of some kind of arbitrary rotation in this way. The point is that if your cross section is not circle or a tube, you've got to put some time into this. These are not hard. It's just that I'm telling you that it matters and you can't close it. And it's important because an I-beam that is on this roof is in a very specific orientation. That's the whole purpose of the I-beam, to make it, use it in that orientation. Don't turn it 90 degrees. Okay? Any questions here? The fact that, look at the coordinate system in that screen. Y and H is perpendicular to the direction of the beam. That allows you to figure out intelligently what these dimensions are. In all likelihood, if my beam was kind of nice and rectangular like that, rectangle, what do you say? Rectangle, 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 rectangle. And then this is the one that I want because it looks like that's what I have. You see that? Rectangle going all the way around. Okay, so that's this. Any questions? Okay. Let me close this. Role of the orientation point, external force, external locations. Okay, let's go back to the same problem. I'm going to delete these. We'll use circular one. Okay, so I don't need these things. You can leave it there. There's no problem. They're not going to bite you. It's just they're not used. Okay, so suppose I want to put my load not at this end, but here, somewhere in the middle of that. Somewhere in the middle of that top horizontal piece, or somewhere on the vertical piece. It's not that easy. No, you can say it's not that easy. There are certain things you have to do. Because we can pick the ends, the points that are on this object. There is this point. I'm sure we can easily put it there. I'm sure we can put it there, etc. Let's try it. So first of all, let's go to generative structure analysis. These are not going to do anything. Just let it sit there. Mesh it. Okay. And give it a cross section. We use circular, cylindrical. Radius is 1, same thing that I did before. There we are. You know what? Let me make it smaller so that you can see things better. 0.25. How about that? 0.25. Just so that it's not that big. That's all. Okay, good. The bottom was clamped. No problem. And I'm going to apply a force. We know that we can apply it there. Can we apply it at this other point? We can probably apply it there. I did it. Let me put it in the direction that I want. 2000 in direction X. Make this thing 0. No problem. If you want minus, I'll put it negative sign there. Okay, good. I can put it at this location because there is a vertex there. But I cannot put it anywhere else. It just won't let me pick it. I just look. Cancel. Load. When I try to pick this, the whole piece is taken. So the question is, if you want to apply it at the specific location that you want, how would you do the problem? Okay, so let me kill this. I don't want this. I can salvage it from here, but I'd rather go there. So first of all, let me create a point there. You have to know where the point is. Okay, so let me go and create a point there. And the way to do it, you go create a point, not with coordinates, on a curve. That's easier for me. It says where on this curve. Okay, is that good? See that blue dot there? A point on a curve. I went and picked the curve, and I can type the coordinates now, or I can drag it until where I want. So we say, okay, that's good, perfect. So a point has been created on that curve. You might think, okay, no problem, I'm going to mesh this thing, and then I'm going to apply it to that point. Will not work. Because this point is on that curve, but there is no guarantee that there is going to be a node there. Remember, you set the size of the element. You said there's no guarantee that even if there was a node exactly at that location, when you put the load on that point, it will not transfer to the finite element. I told you there's a few things you have to do. I created the point where I anticipate to apply the load later on, but that's not good enough. Not done yet. So then you have to go and measure, make sure that there is a node at that location. So how do we do that? You can't do it in generative structure analysis. You have to go to the advanced machine tool because this is something more complicated. It's not just go there and directly say measure. There's something else that you have to do. So you cannot do those things by just going to generative structure analysis. You go to advanced machine tool. As the name suggests, advanced machine tool has nothing to do with forces, nothing to do with, it has to do with mesh. That's all. Okay? And there are people at Ford and General Motor and these other places, Chrysler, that their job 40 hours a week is do a nice mesh. That's all. They don't even have to be engineers. Okay? But anyway, static analysis. Here's the beam measure. See that? This is the same one that we had before. It's the same thing right there. Click on it. Notice that there is some other stuff here down below. First of all, I select that, no problem. But there is this thing which says, hey, you want a point? Pick it. In other words, you want a node to be at a certain location? Do it right there. It says an isolated point. You click on it. It says, where is it? It's this thing that I created. It guarantees that there is going to be a node there. So when you put the load on it, it goes to the node. Okay? We say okay. We say okay. And even if I hit this thing, I can put a load there. The rest of the problem, you have to go back to generative structure analysis because it's just a mesh. That's it. That's all the. So now we're going to go to generative structure analysis. We already meshed it. Let's do the 1D property. 1D property, a cross section. That has to be done here. You click on it. The support is right there, just like before. The circle, remember, I made 0.25 so that you can see it right there. No problem. I don't need an orientation point because this is a circle. Let's clamp the bottom. Clamp the bottom. It clamped it. Let me apply a force. And now I can go and select this point, and it's going to go on that node that is created there. I'm pretty sure it will. Let's see. Oh, but the direction is wrong. Let me fix the direction. Where is this load? It's in the direction X. I wanted X. Negative 2000, right? And this one is 0. There. Now, don't let it fool you. Without doing this fancy stuff, it probably would have shown this too. But when you try to run it, it says, I don't understand. You can't. It gives you 0 basically displacement. Because I always pray. The fact that it turned yellowish means it's good. Okay, so moved, displaced. Notice the numbers changed. I mean, it's not the same dimension, but all I'm saying is that, let me color this, give a different color for you. Just remember, you put a load there. The steps were like this. Create the point on the geometry. Go to the advanced meshing tool. Insist that that node be transferred to the mesh. That's it. Okay? But you also realize that because the load is put there, this rest of the structure, the rest of the structure here, it goes for a ride. There's no deformation, there's the rest of the structure. It just moves as a rigid body. Okay? This piece does not go through bending. But if you put a load there, at this tip, it will go through bending. I mean, you might say, who cares? I don't know. You said I want to put a load there, I showed it to you. Okay. Any questions? There are other ways of doing this. For example, let me go ahead and kill this. Because you might say that, you know what, this is too complicated for me. So what I'm going to do is the following. Let me close this. And as I said, no, I better not say that. I don't think I've said it. This year I didn't say it. So let's go back to, let's go start, you're almost done. I want to show you a different way of doing the same problem. The load being applied at some point, intermediate, if you know in advance what it is. So on that plane, I will sketch. Same thing that I did before. Look, I go up, I go sideways on a curve, I go there, and suppose I want to apply the load there, click, and then go. So basically, I have created two lines there. I've created two lines. And if I've created two lines, they have ends. And as long as I've created that second line in the right spot, I can apply the load there. Okay, so you can see that there's this line and there's this line. So there is a point there where I want to apply the load. Okay, so exit. Do not forget to join. Apply material. Steel on that part. Okay. Good. I'm going to go to generative structure analysis. There is no fancy stuff of going to the advanced meshing tool and say this point should be on the beam, etc. Say okay. Cross section, circular, same size. Oh yeah. Wait. I'm trying to apply the cross section. It doesn't work. It's not even taking it. Can you guess what it is? Why? I did join it. I think I joined it. I did. But why is it not taking there? Because I haven't even meshed it. Okay, so cancel this. Mesh. Right? You have to mesh it first. There we are. Say okay. Now, cross section. I can select it. 0.25. Remember 0.25? There's 4 of them now because there are 4 segments. Okay. And good. And now clamp the bottom. And load this point that I could not do before. Now I can do that. There is a point here. Right there. And say okay. Let me run it. And you can look at deflection, etc. One last thing. You might say, Well, can I have that top piece, for example, different cross section? Can I have a different cross section on the top one, but maybe a bigger circle? The answer is yes. And what you do is the following. This is constant. When you join, everything is going to have the same cross section. But you can tell it otherwise. I'll show you how. Let me deactivate this plot. Where is this guy? Deactivate this. Go to properties. See that property right there? Property is what gives you the cross section. Remember 1D property? If you put the cursor there and you say right click local 1D property, in other words, you can go and any one of these that has the same cross section locally change it. For example, local property on this guy, this line. What cross section? 0.75 or 1 or 2, I don't know. So if you join, you put a cross section, it's going to be everywhere. But you can change it by going to properties, right click local property, and one by one change it. The only problem is that if one of them is non-rectangular, then you have to go and change the orientation and things like that. Okay, I didn't do too many boo-boos here, so this is going to go on YouTube. Are there any questions?